So I'm going to go through this graphing rational expressions review just to give you an idea of what to expect for the test, and if you had any trouble going through these on your own, this could be a guide to help you out a little bit. So if I'm graphing something that looks like this, I notice it's a quadratic over a quadratic, and hopefully both of those polynomials will factor. And if you use the AC method, that numerator is going to factor into 2x minus 1 times x plus 3, and that denominator is going to factor into 2x minus 1 times 3x plus 2. And you could always distribute that out just to check. Some people use the AC method, some people just guess and check and distribute and make sure they get those original polynomials. But when I do this, I notice that there's a common factor in the numerator and the denominator. So I'm actually going to reduce that before I start the analysis for the intercepts and the asymptotes. And I'm going to say that my original function behaves exactly the same as x plus 3 over 3x plus 2 as long as x does not equal 1/2. And the reason I'm picking 1/2 is because that's the value of x that would make 2x minus 1 equal to 0. And if 2x minus 1 was equal to 0, then this entire fraction would just be 0 over 0, and it very much would not be the same as that. So we'll come back to that when we're trying to set up our graph, but all that means is that there's going to be a hole at x equals 1/2 instead of a vertical asymptote. When I have a factor I could reduce in the top and bottom, that's going to cause a different type of discontinuity instead of that vertical asymptote. So let's get all of our pieces together. For our y-intercept, remember that's when x is equal to 0. So you could probably do this by inspection. But if I plug in 0 for x, you might notice that everything that has an x in it is just going to go to 0. So all we're left with for a y-intercept is the ratio of whatever the constants are in the numerator and the denominator. So our y-intercept here is going to be 0, 3/2. For our x-intercept, that's whatever x value makes the output for this function equal to 0. And essentially, we could just set the numerator equal to 0, because anytime we have 0 over any number that's not 0, that's going to cause the entire output to be 0. Alternatively, some people look at this equation and they multiply both sides by 3x plus 2. You can do that. And then 0 times 3x plus 2 is just 0. And then you could just look at this and say that x equals -3 would be our x-intercept. So essentially, -3, 0 is where this graph is going to cross the x-axis. Now, for our vertical asymptote, that's after we've reduced any common factors in the numerator and denominator, what value or values of x would make that denominator equal to 0. So essentially, when would this be undefined and not have any output at that particular x value? Well, in this case, if I minus the 2 and divide the 3, I think that's going to be at x equals -2/3. And again, that's not a coordinate, that's a vertical line where there's going to be a vertical asymptote. So the last thing I'm going to find here is I'm going to try to determine what the horizontal asymptote is. Now, I know there's a horizontal asymptote instead of a slant asymptote because the degree of the numerator is the same as the degree of the denominator. They're both of degree 1, which means for very large values of x, they're going to eventually end up growing at similar rates. In terms of a technical sense, this is defined to be a limit as x approaches infinity or as x gets very, very large. Now, I recommend doing this by inspection instead of doing this algebraic portion, and you could use the original, or I'd recommend the reduced form since you have less to look at here. And I noticed that for very large values of x, those constants of 3 and 2 really aren't going to make much of a difference. So this is going to eventually behave very similarly to this function right here, which is exactly the same as the line y equals 1/3 for very large values of x. The algebraic portion of this, if you wanted to show some work, would be to multiply the numerator and the denominator by 1 over whatever the highest power of x you see is. In this case, the highest power of x I have is just 1. So I can equivalently rewrite this as the limit as x approaches infinity of, well, 1 over x times x would just be 1. 1 over x times 3 would be 3 over x. And if I do that same process in the denominator, I'd have 3 plus 2 divided by x. So I'm trying to examine what happens to this quantity as x increases without bound. And if I'm thinking about 3 over x, 3 divided by some increasingly larger number, that's going to go off to 0, because 3 divided by something very, very large is going to be a number that's very, very small. You can make a similar argument for 2 over x. So essentially, I would just have a 1 left over in the numerator and a 3 left over in the denominator. So I would know that the y value that this function will increasingly approach for very large values of x is y equals 1/3. So that's going to be my horizontal asymptote. Now, you can do that as x goes to negative infinity as well, and you should come to a similar conclusion on the left-hand side of the graph. So let's try to put all these pieces together, right? Because this should force the curve to look a particular way. I'm going to give myself a nice y-axis and x-axis here. It doesn't have to be scaled particularly nice, but it should have all the asymptotes and intercepts labeled. So I'm going to start by putting up a barrier right there, because I know there's going to be a vertical asymptote at x equals negative 2/3. And I know there's going to be a horizontal asymptote at y equals 1/3. So it's positive, a little bit above the x-axis there. The next thing I note is that my y-intercept is above the horizontal asymptote. It's at 0, 3/2. And then the only other point that I've determined is on this function is negative 3, 0. And that forces what these two parts of the curve are going to look like. So I'm going to draw them in. Of my left part of the curve would have to approach my asymptote as it goes to the right, and it's either going to go up or it's going to go down, but the reason it would have to go down here is because the left-hand side would have to approach that horizontal asymptote as x goes off to negative infinity to the left. You know, I know it can't look like this because it has to have that x-intercept of negative 3, and specifically that intercept of negative 3, that root only has a multiplicity of 1, so it's not going to bounce at that point. It's going to cut straight through the x-axis. Now, for my next part of the function, because my y-intercept is above that horizontal asymptote, I would say it has to look something like that. So this function is going to look almost like this. But there's one exception of, based on our original analysis, there's going to be a hole at x equals 1/2. So that's actually a really easy fix. I'll just maybe mark an x value of 1/2, and then I'm going to go up to my function, and this is why we sketch in pencil, for instances like this when that happens. And I'm just going to draw an open circle there. That's saying that our function is defined for every value of x in that vicinity except for 1/2. If I wanted to figure out what the y value of that coordinate is, what I would have to do is I would have to go to my reduced rational function here, and I would have to substitute in 1/2 for x, and then whatever that output would be, that's the y value where that hole occurs. I'm not going to simplify that here, but just know that's how I would find where that value occurs. For number 2, this is still a quadratic divided by another quadratic, but I'm still going to try to factor everything before I find my intercepts and my asymptotes. And both of these are just regular AM methods. I think the numerator is x minus 3 times x minus 3, and the denominator would be x plus 3 times x plus 3. Alright, so I'll do the same analysis for the y-intercept, x-intercept, and so on and so forth. For your y-intercept, I'm going to do this off the top of my head. Again, remember, everything that has an x in it, if I substitute in 0 for x, is going to go to 0. So my y-intercept is just going to be whatever 9 over 9 is, which is 1. Because you don't have a calculator, you should be able to do most of these by inspection. For my x-intercept, again, you could set the whole rational expression equal to 0, but I know I really just care when the numerator equals to 0, because the entire output would be 0. And I only get one root here, but I need to keep in mind that because that factor appears twice in this equation, and it is a quadratic, I should get 2 solutions, that this root is going to have a multiplicity of 2. And try to remember what that's going to cause in your graph. That's going to be some sort of bounce, either bouncing up or bouncing down, but it's going to be tangent to the x-axis at that point. Okay, so my vertical asymptote is still whenever my denominator equals to 0, whatever value or values of x would cause this fraction to be undefined. And I think here it would just be -3. Do note that that factor appears twice in our denominator. That also will have an interesting effect on the graph, where at that vertical asymptote, instead of going in opposite directions, usually the case is they go in the same direction, whether they both approach infinity or whether the y values approach negative infinity on either side, like this and like this. Usually that's what happens when you see that factor twice in your denominator. Alright, so that's our vertical asymptote. And again, I know there's a horizontal asymptote here because my numerator and my denominator are of the same degree. It's a quadratic divided by another quadratic. You could do the algebra for it, but if I'm looking at the limit as x approaches infinity of x squared minus 6x plus 9 over x squared plus 6x plus 9, I'm just going to take the ratio of these coefficients of highest powers. I know if I go through the algebra, that's going to approach y equals 1 for large values of x. And that's, you could multiply everything by 1 over x squared if you wanted to. That would maybe convince you a little bit more. Or, the informal argument is that for very large values of x, those constants aren't going to make much of a difference. And for even larger values of x, a quadratic, or that x squared, is going to be so much larger in value than a constant times whatever that input was, that these 6x and these minus 6x's aren't going to make much of a difference for very large values of x, like 1,000,000 or 1,000,000,000, right? 1,000,000,000,000 squared is a huge number compared to 6 times 1,000,000,000,000. So with all these pieces, I'm going to try to put this together. So I'm going to move these down here. And I'll give myself a nice big x and y axis. And I know there's a vertical asymptote at -3, so I'll plot that in here. And again, anytime I include an asymptote or an intercept, I'm going to include a label. And there's a y value of 1 that this function is going to approach on the right-hand side and the left-hand side. Additionally, I know I have an x-intercept at +3. So let's say right here. And I have a y-intercept of 1. Now, notice your graph is going to cross the horizontal asymptote here. That's okay. Your graph can cross the horizontal asymptote as many times as you want. There's no rule that says you can't cut through that. However, for very large values of x moving to the right and to the left, it should look like it's approaching y equals 1. So by process of elimination here, if I'm trying to figure out what the left part of the curve looks like, there's no way it could be this, right? And let's try to convince ourselves that's true. If that were to be the case, there would be another x-intercept, but our previous analysis shows us that there is only one x-intercept, so I think that can't be the case. So the only thing that this left part of the function could look like is something that shoots up to infinity as we approach -3, and then goes off to +1 as we plug in bigger and bigger negative values for x. So for the right-hand side, I can't come up to get to that y-intercept of 1, because again, then I would cross the x-axis one more time than I want to. So my only option would be to come from above and then hit the x-axis here. And keep in mind, I can't go through the x-axis, because if I go through the x-axis, I'd have to come back up to approach the asymptote and again create another root that I don't want to have here. And I recognize that this root should have a multiplicity of 2, which means it should be tangent to the x-axis at that point. So I'm going to curve it back up and then have it approach that asymptote as we move to the right there. So these are some of the funkiest ones to graph because they don't have nice symmetry, but it still satisfies all four of these conditions. It's got a y-intercept at 1, it has an x-intercept at 3, vertical asymptote at -3, and a horizontal asymptote at 1. You could always graph this in your calculator and check to make sure it looks something like this when you're doing this on your own, but on a test you'd have to have the confidence that this is what a particular rational function can look like. All right, for number 3, we're going to graph y equals x squared divided by x squared minus 16. Again, another quadratic over a quadratic. And I'm going to very quickly get the y and x intercepts. The y-intercept I would get from setting x equal to 0, which in this case would just be 0 over -16, or 0. So my graph will pass through the origin, which narrows down what our x-intercept should be. But if I set that numerator equals 0, keep in mind the degree of that equation is 2. So even though I get 0 as a root, which I know because it goes through the origin, it's still going to have a multiplicity of 2. Because it's x squared, that linear factor of x appears twice here. So I know that's going to cause a bounce at 0. My vertical asymptote I get from setting my denominator equal to 0, and I probably should have factored this first, right? If there is a quadratic, generally it will be factorable. And I recognize that this is a difference of 2 squares. So there's actually 2 unique values of x that would make the denominator equal to 0 here. Which means that in my graph there's going to be 2 vertical asymptotes. So I want you to think about how many different parts of the curve you'll have to write here. If there's 1 vertical asymptote, there's 2 parts of the curve. So if there's 2 vertical asymptotes, or 2 breaks in the graph, then there should be 3 parts of the curve you're going to have to graph all together. And for my horizontal asymptote, again, the degree of the numerator is the same as the degree of the denominator, and I could just take the ratio of the coefficients of those highest powers. So if it's a 1x squared over a 1x squared, 1 over 1 is eventually going to trail off to y equals 1. So putting all those pieces together, there has to be 2 vertical asymptotes here. One at x equals -4, and one at x equals +4. And you might notice that I'm again using dashed lines here. These technically aren't part of my graphs. I'm just putting them in to put up some barriers so I don't go past them, and I know I should shoot up and down to infinity at those lines. So then for my horizontal asymptote, that's going to be at y equals 1. So it doesn't matter where you start here. Let's start with the left-hand side of the graph and we'll move to the right from there. Again, my only x and y intercept is at 0, so there's no way it could do something like that. So instead, it would have to exist above the horizontal asymptote, shooting up to infinity as we move to -4, and shooting closer and closer to y equals 1 as we move to the left there. Now in the middle we've got 2 options. I recognize that root of 0 has a multiplicity of 2, so it could look like this, maybe something like that. Or it could look something like this where it curves down on both sides. Those are my only options because it needs to bounce at that point. It can't look something like this because that root doesn't have an odd multiplicity. So if we think for a minute, the easiest way to determine if it should be positive outputs or negative outputs would be to go to the original function, x squared over x squared minus 16, and just pick a test value. Right, there's so many values between -4 and 4 that you could plug in. I'm just going to plug in 1 and see what the sign of my output is, and that will tell me if all of my output should be either below or above the x-axis. So you could probably do this in your head, but when I plug in 1, I get 1 over -15, which is in fact a negative output, so that's telling me the middle part of the graph would have to look something like that. Even if I plugged in -1, you're going to get the same conclusion. -1 squared over -1 squared minus 16. That would still be 1 over -15 or -1/15. So I know all of these outputs, with the exception of the origin, should be negative. And again, just to finish off that third part of my curve, I know it's going to look something like that by process of elimination. I know it can't look like that, and I know it should approach that horizontal asymptote as we move to the right. So that's generally how we can deal with something that has two vertical asymptotes. Now for number 4 here, I recognize that this is something that will not have a horizontal asymptote because the degree of the numerator is 1 degree higher than the denominator. So that numerator is going to grow faster at some point than the denominator will. So this will continue to shoot off to infinity for very large values of x. But it's going to form a specific pattern because the difference of these degrees is 1. That's what causes a slant asymptote, or this function to look like some diagonal line for very large values of x. All the other parts are still just as easy to find. The y-intercept, in this case, would be, I think this should be 2x plus 6. That's what that should be. Let me just fix that real quick right here. So that should be 2x plus 6. Right, for my y-intercept, I can take the ratio of those constants at the end. And I'll reduce that, so 3 halves. So I know 0, 3 halves is 1 point on this graph. For my x-intercept, I would set my numerator equal to 0. And again, you should factor this beforehand to see if anything cancels. The only reason why I'm not is because I know off the top of my head nothing will. So x minus 3 times x minus 3. Oh boy, we have another root with a multiplicity of 2. Keep that in mind of what that will affect on the graph. And my vertical asymptote is whatever x value will make the denominator equal to 0, which in this case is just negative 3. Now here's the new part. I'm not going to set up a process to find the horizontal asymptote because there is no horizontal asymptote. Instead, I'm going to set up some polynomial division to find what the slant asymptote would be. So I'm going to use reverse tabular. I just think that's the most organized method to do the division, but of course if you have another method you prefer, you could use that as well. So I'm going to put my divisor on the right-hand side, my dividend along these diagonals, and I'll start with x squared right here. And to get what goes in the margin here as the first part of my quotient, I'd ask myself, what do I multiply 2x by to get x squared? Well, I would need the coefficient to be 1, so I would have to have 1 half. And to get an x squared, it would have to be x, so 1 half x or x over 2. The reason I'm writing it as 1 half x is because I recognize that my slant asymptote should be a line. So I'm going to try to get it in that slope-intercept form, just to make it easier to plot. Okay, so 1 half x times 6 would be 3x. And then I look along this diagonal, and I know these two boxes need to sum up to negative 6. So if I already have 3x, I would need a negative 9x right here. Next, I ask myself, what would I multiply 2x by to get negative 9x? Well, that would just be negative 9 halves, or negative 4.5. And I'm actually going to leave this box blank because we're done at this point. It does not matter what the remainder is. If you think about what this division would look like, right? We're saying that, let's say there's some remainder here for 2x plus 6. We're saying that this original rational function can be rewritten like this through the magic of polynomial division. But really, I'm just concerned with what happens as x gets very, very large. And as x gets very, very large, that remainder part is going to be some constant divided by an increasingly large number that's also going to go off to 0. So instead, I'm going to label this as my slant asymptote and say that for large values of x, this function is going to start to look just like that line with a slope of 1 half and a y-intercept of negative 9 over 2, or I'll write it as negative 4.5, since I'm going to try to plot that, and that might be a little bit more meaningful to me than an improper fraction. So let's put those pieces together. All right, I'm going to give myself same x and y plane we've been working with. I'd recommend using a straight edge. And I'm going to start with my asymptotes. Vertical one at x equals -3. And the slanted one, I know will cross the x-axis, or excuse me, the y-axis at -4.5. And it's got some positive slope. So I'm not scaling my axes here. You should when you're sketching your own. But just to get a rough draft of this, maybe my slant asymptote would look something like this. And I'm going to include a label on it too, just to show where it falls in the xy plane there. So that's 1/2 x minus 4.5. All right, so I still have a couple of intercepts, right? I've got a y-intercept at 0, 3/2. And then I've got an x-intercept at +3. That's going to be a bounce. So I can't be, shooting down to this asymptote on the right-hand side here. So instead I'm going to be coming down from it. That has a multiplicity of 2, so I'm going to have to bounce away from the x-axis. And for large values of x, it should look like it's approaching that slanted asymptote there. So notice on both sides of my function, on the left-hand side it's approaching that vertical asymptote, and on the right-hand side it's approaching that slanted asymptote. So the other part of your graph is going to be in the opposing side of those asymptotes. So in this case, as long as you left yourself enough room, it should look something maybe like, let me try again. Maybe something like this. It doesn't need to be perfect. You don't even need any points label on there. You just need to know that the other portion of your curve exists over there. Are there functions where, technically could they be over here? Sure. But can that happen for this case? Well, no, that would again have another x-intercept, and we know that can't happen. If you're trying to think of what the other cases could be, could your function, be down here? No, that can't possibly happen either, because then it wouldn't be a function, because each input would go to 2 different outputs. So usually you'll have enough information to pinpoint exactly where the other portion of your function should exist. So that's for something with a slanted asymptote. You might also have to write the equation from a graph. And I'd start by analyzing wherever your vertical and horizontal asymptotes are. So in this case, it looks like there's a vertical asymptote here. I'm going to label that in. And another vertical asymptote here. That's going to inform what factors are in my denominator, right? Because when my denominator is equal to 0, that would cause a vertical asymptote. Now, be careful with your scaling. These just go by ones. That's not to say that's always going to be the case. But I think at x equals -2 and x equals +2, those are my vertical asymptotes. So the factors that should appear in my denominator will be x plus 2 and x minus 2. Now, the next thing I notice is that there seems to be a horizontal asymptote up here at y equals 2. So I know that my numerator is going to have to be of the same degree of my denominator. So I know it's going to have to be some quadratic. Can't be a linear polynomial, because if I had a linear divided by a quadratic, that's going to trail off to 0, not 2. Moreover, I know the ratio of the coefficients for my 2 quadratic terms should be 2 over 1. Right? If I distribute that denominator out, that would be x squared minus 4. And I would take the ratio of these coefficients to get what my horizontal asymptote would be, and I need that to be 2. There's just one other issue here. They tell us that the y-intercept is -0.5, and moreover, there is no x-intercept here. So there's no way this function could possibly represent this graph, because this function would have a root at x equals 0, and that's very much not the case here. So if I need my y-intercept to be negative 0.5 or negative 1/2, that would mean that the constant in my numerator would have to be 2. And let's examine why that's the case. Imagine if you are finding a y-intercept. You're setting x equal to 0. So it would, again, just be the ratio of those constants, and 2 over negative 4 is negative 1/2. So I think this would be a better fit than this to model this graph right here. It has a y-intercept of negative 0.5, 2 vertical asymptotes at x equals negative 2 and x equals positive 2, and a horizontal asymptote at y equals 2. So that's how we would analyze this. We'd start with the asymptotes and then go to whatever intercepts we had. If we, for example, needed to have particular x-intercepts, like let's say x equals 5 was an x-intercept that I needed to occur in my function, that means that in the numerator of that function, a factor of x minus 5 must appear somewhere. So if I had roots to work with, that would help me out with the denominator. If I have vertical asymptotes, that's what helps me out with the denominator here. So for the last one, number 5, I want to draw a function p of x such that p of x has a vertical asymptote at x equals 1, a slant asymptote at x plus 2, and then some y-intercept that's at negative 5. So I'm going to do a real rough sketch of that, and then we're going to try to determine that equation. All right, let's see, vertical asymptote at x equals 1, slant asymptote at x plus 2, so that's some positive sloping line with a positive y-intercept. And then the y-intercept of the function I'm looking at is going to be a negative 5. And again, this is just a real rough sketch to get an idea of what it looks like. But maybe it would look something like that, and something like that. So maybe this comes up and hits the x-axis. I don't really know. It doesn't give me enough information to determine that. So let's just try to take this information and determine an equation for it. Well, again, an equation. First off, it's not going to be y equals in this case because they want me to draw the graph of p of x, so they've given me a particular label here. So I'll make that p of x. And I know my denominator should be x minus 1. The reason I know that is my vertical asymptote is at x equals positive 1, so positive 1 would make this denominator equal to 0. The next thought that I have is, well, how do I get my numerator? Well, they gave us a slant asymptote. And try to think about how we get a slant asymptote. We get a slant asymptote from dividing the two polynomials. Specifically, from dividing the denominator and the numerator. So if I'm missing what one part of the division was, I can simply multiply x minus 1, my divisor, and that slant asymptote, and that should give me some idea of what this numerator is going to look like. So just real quick, I'm using the box method here. You don't necessarily have to, but the quadratic term should just be x squared, the linear term should just be positive x, and now this constant, even though when I multiply x plus 2 times x minus 1, and I get x squared plus x minus 2, there's no way that could be my numerator, because this function would have a y-intercept of positive 2. That's not what I wanted to get here. I wanted to have a y-intercept of negative 5. So to fix that, I can just make the constant in the numerator positive 5, such that if I were to substitute in 0 for x, these would reduce to negative 5. Because it doesn't actually matter what that number in the bottom box is, because remember, you're going to have some sort of remainder when you do this division, and that's not going to affect what the slant asymptote is, because for very large values of x, that remainder part is going to go off to 0 anyway. So that constant in the numerator can be whatever I need it to be to make the y-intercept whatever point they give me. And I might not even give you the y-intercept. I can give you any point on the graph, and that should inform what that constant has to be.